21.4. The Carnot Engine. In this session, we will explore the fundamental principles of the Carnot engine. Our discussion begins with an introduction to Sadi Carnot and his theoretical contribution to thermodynamics. We will then examine Carnot's theorem and the efficiency limits it imposes on heat engines. Following this, we will break down the four specific processes that make up the Carnot cycle and illustrate how they appear on a pressure-volume diagram. We will also calculate thermal efficiency and discuss the practical implications of these concepts, including their application to heat pumps. Sadi Carnot was a French engineer who lived from 1796 to 1832. In 1824, he published his landmark work titled Reflections on the Motive Power of Heat. Carnot was the first to establish a quantitative relationship between work and heat, moving beyond simple qualitative observations. Interestingly, he defined work in a very practical sense as weight lifted through a height. His theoretical engine serves as the foundation for our understanding of how efficiently energy can be converted into useful work. The Carnot engine is a theoretical construct that operates in an ideal, reversible cycle known as the Carnot cycle. It functions between two energy reservoirs, one hot and one cold. This engine is significant because it is the most efficient engine possible for any two given temperatures. By defining this ideal performance, the Carnot engine establishes a fundamental upper limit on the efficiencies of all real-world engines, providing a benchmark that no physical machine can ever exceed. Carnot's theorem formalizes these efficiency limits. It states that no real heat engine operating between two energy reservoirs can be more efficient than a Carnot engine operating between those same two reservoirs. Crucially, the theorem reveals that the efficiency of a Carnot engine depends only on the absolute temperatures of the reservoirs themselves, not on the working substance used. Under these ideal conditions, the net work done is the greatest possible for a given energy supply. To prove that the Carnot engine has the maximum possible efficiency, we use a proof by contradiction. We start by assuming an engine exists with an efficiency greater than the Carnot efficiency. If we connect this hypothetical engine to a reversible Carnot heat pump and match their work outputs, we create a system where the net work is zero. However, this configuration would result in a net transfer of energy from the cold reservoir to the hot reservoir without any external work. This directly violates the Clausius statement of the second law of thermodynamics, proving our initial assumption was impossible. The Carnot cycle consists of four distinct stages. The first stage, process A to B, is an isothermal expansion at the hot reservoir temperature. During this step, the gas is in thermal contact with the hot reservoir, absorbing heat while expanding and doing work to raise a piston. The second stage, process B to C, is an adiabatic expansion. Here, the cylinder is thermally insulated, so no heat enters or leaves. As the gas continues to do work and expand, its temperature naturally decreases from the hot reservoir temperature to the cold reservoir temperature. The cycle continues with the third stage, process C to D, which is an isothermal compression at the cold reservoir temperature. The gas is placed in contact with the cold reservoir, expelling energy as heat while the piston does work on the gas. The final stage, process D to A, is an adiabatic compression. The cylinder is once again insulated, and the temperature of the gas increases back to the starting hot reservoir temperature as work is done on the gas. This returns the system to its initial state to begin the cycle again. A pressure-volume diagram, or PV diagram, provides a visual representation of these four processes. The path consists of two adiabatic curves and two isothermal curves. Because every step is reversible, the path can be traced in either direction. The net work done by the engine during one full cycle is equal to the area enclosed by the path on this diagram. Mathematically, this net work is also equivalent to the magnitude of the energy absorbed from the hot reservoir minus the magnitude of the energy expelled to the cold reservoir. The efficiency of a Carnot cycle is determined by the ratio of energy transfers. Specifically, the ratio of the magnitude of heat expelled to the cold reservoir divided by the magnitude of heat absorbed from the hot reservoir is equal to the ratio of the cold reservoir temperature to the hot reservoir temperature. Therefore, the Carnot efficiency is defined as 1 minus the ratio of the cold temperature to the hot temperature. This shows that 100% efficiency is only possible if the cold reservoir is at absolute zero, which is physically unattainable. We can prove the efficiency relationship by looking at each step of the cycle. For the isothermal steps, the heat transfer is proportional to the natural log of the volume ratios. For the adiabatic steps, the temperature and volume are related by the constant gamma. By dividing the adiabatic equations, we find that the volume ratio of the expansion matches the volume ratio of the compression. This allowed us to simplify the heat ratio into a simple ratio of the absolute temperatures, confirming the mathematical basis for Carnot efficiency. Let us look at a practical example involving a steam engine. If a boiler operates at 500 Kelvin and exhausts at 300 Kelvin, the Carnot efficiency is calculated as 1 minus 300 divided by 500, which equals 40%. If we want to increase this efficiency, decreasing the cold reservoir temperature by 50 Kelvin results in an efficiency of 50%. In contrast, increasing the hot reservoir temperature by the same 50 Kelvin only yields an efficiency of about 45.5%. This demonstrates that lowering the cold temperature is mathematically more effective. A Carnot engine run in reverse acts as a highly effective heat pump. We measure its performance using the coefficient of performance, or COP. For heating mode, the COP is the hot temperature divided by the difference between the hot and cold temperatures. For cooling mode, it is the cold temperature divided by that same temperature difference. As the temperature difference between the two reservoirs approaches zero, the theoretical coefficient of performance approaches infinity, though real-world mechanical limits prevent this in practice. It is important to remember that the Carnot engine is an idealized model and not a design for commercial use. Reversibility requires processes to happen infinitesimally slowly, which means a true Carnot engine would have zero power output. Real engines always lose efficiency due to friction, thermal conduction, and turbulence. To better approximate real engines operating at maximum power, we often use the Curzon-Alborn efficiency, which is defined as 1 minus the square root of the ratio of the cold temperature to the hot temperature. In summary, the Carnot engine represents the theoretical maximum efficiency for any heat engine. This efficiency depends solely on the absolute temperatures of the hot and cold reservoirs, calculated as 1 minus the cold temperature divided by the hot temperature. The cycle itself is composed of 2 isothermal and 2 adiabatic reversible processes. Reversibility is the defining feature of this cycle, allowing it to set the fundamental physical limits for the field of thermodynamics. To wrap up, consider these 2 review questions. First, why does a Carnot engine have zero power output even though it is the most efficient engine possible? Think about the time required for reversible processes. Second, can you explain mathematically why decreasing the cold reservoir temperature increases efficiency more effectively than increasing the hot reservoir temperature by the same amount? Reflect on the fractional changes we observed in our steam engine example.